Hi, welcome to the walkthrough for problem 3 of the fall 2025 midterm. In this problem, we're given a data set of n points of the form x comma y, and we're also given the mean of the x's and the mean of the y's. Additionally, we're given a new set of values z, where each z value is based off of the x's and y's. Specifically, we're multiplying each x value by 3 and then subtracting its corresponding y value from it. So, if we fit a simple linear regression model where we use the x's to predict the z's, what is the prediction for 15 going to be? Well, we know that the mean of the x's is 15, and we also know that the prediction for the mean of the x's should be the mean of the z's. That's because the simple linear regression line is guaranteed to pass through the point of the mean of the x's and the mean of the z's. So the question is, how do we find the mean of the z's? Well, we can write this directly using the definition of the mean, but applied to what we know about z from the problem. We can expand out the sum and its 1 over n coefficient. And this term right here is just the mean of the y's. And then if we pull out the 3 here, that's just going to be 3 times the mean of the x's. We plug in the values for the mean of the x's and the mean of the y's, giving us a prediction of 40. The next part of the problem gives us the variance of the z's, but in terms of the variance of the x's, 9 times the variance of x, the variance of the y plus the variance of the y's, and then plus some other term c, and we're asked to find the value of that term c. So it makes sense here to start with the variance formula for z, which is going to be 1 over n times the sum of each z's distance from the mean of the z's squared. So since we're trying to find it in terms of the variance of the x's and the variance of the y's, it makes sense here to substitute in the definition of z from the beginning of the problem, where it's in terms of x and y. Now we can distribute the minus sign. And we have something like this. So the question is, how do we go about simplifying this further? Well, let's start by grouping together our like terms. And specifically, we're going to pull out a minus sign here from the minus yi plus y bar for a reason you will see very shortly. So when we're working with anything squared, we know that if we have a minus b and we square them, then the result is going to be a squared minus 2ab plus b squared. We can apply that same idea here, where our a is going to be the entire first term of 3 times xi minus x bar, and then our b is going to be the whole yi minus y bar term. So now this allows us to expand out to the square. So now that we've expanded out the square, what can we do from here? Well, let's start by breaking apart the sum and see if we can get anything from breaking apart the sum and trying to relate it back to the original definition for the variance of z. So now that we have it written out like this, we can pretty clearly see that the first term is just 9 times the variance of the x's, right? Because we can just pull this 9 out of the summation. It's just a constant factor. And then the last term is the variance of the y's, which is just like our formula from above, right? We have 9 times the variance of the x's plus the variance of the y's plus something c. In other words, this middle term right here, this minus 1 over n times the sum of 6 times xi minus x bar times yi minus y bar, this is going to be our c. And so we want to simplify this term further. How are we going to do that though? Well, we can actually use the definition of the correlation coefficient here. The correlation coefficient is defined as 1 over n times the sum of each xi minus x bar divided by the standard deviation of the x's times each yi minus y bar over the standard deviation of the y's, right? Well, if we multiply both sides by the standard deviation of x and the standard deviation of y, we can cancel out the terms on the denominators inside of the sum. Leaving us with a term that looks very similar to what's happening over here inside of C. The only difference here is the 6, but we can just pull the 6 out of the sum because again, it's a constant factor being multiplied to every single term in the sum. So once we substitute this back in, I'll write this out a little bit more formally first. C equals negative 1 over n times the sum of 6xi minus x bar yi minus y bar 1 over n times 6, or rather 6 times negative 1 over n This means we can substitute this now into negative 6 times r times the standard deviation of the x's times the standard deviation of the y's as our final answer for C.